This is lesson 1.3, which is force vectors. So what is force? Well, it's a push or a pull on an object. So think about if you're pushing, say, a shopping cart, or you're playing tug of war and you're pulling on that rope. Each of those examples exhibits a magnitude. Okay, so that is a force that's measured in newtons, and so we use a capital N to denote newtons. They also both have direction. So think about it. If I push a shopping cart, it's going to go in a certain direction. If I pull on that rope and someone else is tied to it, well, they're going to come flying in my direction. Okay, so magnitude and direction together are the components for a vector. Now, a force vector also has a point at which it's applied. So you're going to apply the force onto an object at a specific position. Okay, so last video we talked about something called a resultant vector. And remember that a resultant is when you have several vectors together and they create a result. Okay, like you add them together and they make a resultant vector. You can have the same thing when you're talking about force vectors. You can add several force vectors together to get a single force. So for example, if I got some of my buddies together and they were going to help me move like a couch, well, all of us are going to push, so we'll be the individual vectors all pushing together, and in total you're going to get that single force vector that's going to push the couch a certain way. So that's where movement happens. Now, when movement doesn't happen, everything is said to be in equilibrium. So that is a state of rest where everything kind of cancels each other out and you get a zero vector. So for example, if you had several vectors going like this, but instead it returns back to the original position, well, you didn't really go anywhere. That's what an equilibriant vector is. Okay, so this guy right here is called an equilibriant vector. It's where all the arrows are kind of going in a circle, and so they all cancel each other out and you get zero. So if you kind of take a look, like the resultant vector is actually the opposite of the equilibriant vector. In fact, you can kind of write it like this, where you have the resultant hook, okay, and that's equal to the negative equilibriant vector. All right, so this video is going to go over several examples of equilibriant and resultant vectors. So our first example is Kajal and Jana are pulling two ropes attached to an ice hut. Okay, so here we have an ice hut. I have K with a vector symbol representing Kajal's force. Notice it has an arrow, and then also Jana's force. Okay, they are pulling at 35 degrees, which I've written right here, to each other with forces of 15 newtons and 12 newtons respectively. So that means K is going to be 15 newtons, the magnitude, and then the magnitude of J is going to be 12 newtons respectively just means whatever order they had written it in is going to be the order for these two numbers. Now on a test, you won't get marks for this. This is just to describe what we kind of read. What we will get marks for is something called a vector diagram. And so a vector diagram is a little bit more specific, and let me show you what it looks like. So a vector diagram obviously needs vectors. Okay, so I'm going to redraw these, and we're going to put them here. Okay, we're going to be a little bit more specific when we put the numbers in. So when we say K is 15 newtons, we don't write it like that. Like, that doesn't even make any sense. How can an arrow have 15 newtons? Because it has direction to it as well. All you wrote is the magnitude. So if you really want to be specific, you want to get those marks on a test, make sure that you have the magnitude symbol and you're telling me the magnitude of this vector is 15 newtons. And the magnitude of this vector is going to be 12 newtons. The angle in between is 35 degrees. Now what the question is asking you for is how this ice hut is going to move. Well, if two people are pulling it in these directions, obviously it's going to probably move this way. But does it move straight? Like, does it move this way? Does it move this way? How am I supposed to know? And by how much? So what we're going to do is, because it's moving, we know we're trying to find a resultant with a certain magnitude and direction. Okay, now let's focus on the magnitude first. I need to find the resultant, but from our last video, we saw that the resultant wasn't where you have a tail-to-tail situation. It's where you have a tip-to-tail situation. So you can only draw it when they're tip-to-tail, which means I'll probably have to move this. Let's draw it again over here. Okay, and let's see if I can I move this? Oh, I'll move everything. Okay, never mind. I'll write it again. Okay, so this is J, 12 newtons. All right, now that we have things tip to tail, I can draw the resultant. This is, well, it doesn't really matter which order it goes in, but I have a little bit of OCD. K plus J, yeah? And then we want to find the magnitude of it. All right, so that's starting to look a little bit like a triangle, which is great because with triangles, I can use trig. Okay, the only thing is I don't think I have enough information yet. So the 35 doesn't look like it's inside the triangle, and I really need an angle inside the triangle in order to use some trig. So what I'm going to do is I'm just going to extend this and see this 35. Well, it'd probably be over here as well because of corresponding angles. Okay. And if I have a 35 there, well, I know that these guys are supplementary. So theta should be 180 minus the 35, which should be 145. Okay, score. I got 145 inside my triangle, which means I can do cosine law. All right, so cosine law is at the bottom in green, and I found out the resultant is 25.8 newtons for the magnitude. Okay, when we describe a vector, so the resultant vector, it has a magnitude, which I have in green, but you also need a direction. So how do we describe the direction that the ice hut is moving? Well, what I would do is I would say, since it started here, I'm going to say it moves in this general direction, but at this angle relative to K. So I'm going to call this alpha. Okay, so I'm going to find alpha, and then I'm going to say, oh, this ice hut is going to move 25.8 newtons at a certain angle relative to K. So how do we find that angle? Well, I have a pair of angles and sides that are opposite, and so I can set up sine law. And I'm not going to go through the steps. I mean, let's be honest, this is grade 10 stuff. Okay, so the hardest part is actually just drawing the diagram. Okay, so the final answer is the ice hut is moving at a force of 25.8 newtons at 15.5 degrees relative to kJ. Okay, so major marks for this diagram. Less messy though. All right, next question. Example number 2, a welcome sign, which is right here. I don't know if you can see that. It says welcome. With a mass of 8 kilograms, is suspended above a storefront. So this is storefront. And is suspended by 2 wires. So along the wires, because this obviously has a weight to it and it's going to be pulling downwards because of gravity, you have a tension along both of the wires. So they want you to find that tension, and that is a magnitude. Okay, so tension itself, you can have tension vectors, but we want to find the magnitude of them. So again, this is not something that you would get marks for. This is just to put down our thoughts. And it looks like they've given us 2 angles as well. So let's create a diagram where we'd actually get marks, which are vector diagrams. So I'm going to move this guy right down here, and we're going to recreate this. And I want to show you slowly how I'm actually recreating this. We'll call this tension. Oh, I don't know why I did that. We'll call this tension 2. I'll put that right down there. Okay, and then we'll draw another one. I'm just going to fix this one, move that there. That'll be tension 1. By the way, these tensions, they are directed upwards because they are balancing out the gravity. And so gravity creates a force that is going to go down because obviously that sign weighs something. Okay, so those 2 tension forces point upwards in order to balance out that sign. And that means that the sign is not moving anywhere. It's not like the last example. This is an example of equilibrium. Okay, so nothing is moving. Now I'm going to get rid of this. Actually, you know what? Before I get rid of this, let's put in all the numbers. Let's call this our equilibrium force. Okay, and I have tension 1, tension 2. This is 60 degrees, and that is 45 degrees. Okay. This really doesn't cut it either for a diagram, mainly because in order to calculate anything, notice that we've actually been using a lot of triangles. And so we have to somehow move all of these vectors so that they create a triangle. Okay, so bear with me, see if you can follow along. I need to put things tip to tail. So I'm going to take this guy, keep that there. The 45 was somewhere around here. Take this vector, put it tip to tail. There we go. Now that's starting to create some sort of a triangle. That's right there. Okay, and then my equilibrium force, I'm going to grab that, put it right there. And as you can see, like my vectors aren't to scale. Like this diagram that I base these vectors on aren't really to scale. So I'm just going to change them up as long as they're at the same. I mean, technically that's not right because vectors have a certain magnitude to them and you have to show them through their arrows. But like I said, this isn't to scale. All right, so I just want you guys to get the idea. Okay, so there you go. It is a triangle. They all go in a circle, which means that nothing should be moving because the equilibrium is going to balance everything out. It's going to become a zero overall vector. Okay, so your job is to figure out, I'm going to move these guys a little bit farther. Right here, 60 degrees. This is T2. So you're trying to find this guy and this guy. What are the magnitudes of both? All right, now we do have a little bit of information that'll help us to find those two tensions. We have information about the equilibrium. So the force of the equilibrium, and if you think about some of the physics, is mass times acceleration. If I go back to the first slide, you'll notice that this is the mass and this is the acceleration, and they will create a force. Okay, so the mass has to be in kilograms, which I think, whoops, I think they said it was 8 kilograms, and acceleration is 9.8. Okay, which will give equilibrium force of 78. That doesn't even make sense. What am I writing? I don't know what I'm writing. It's late. 0.4 newtons. All right. Now, I need more information inside my triangle, so what I'm going to do is I'm going to start to, start playing with it a little bit. Now, this looks like it should be in 90 degrees because the equilibrium force goes straight down due to gravity. This also looks like it would be a 90 degrees, which would make this a 30 degrees. And this is going to be a 60 degrees because we got a Z like that. Okay. All right, so I'm solving stuff inside my triangle. I got, this is 45 degrees if I fill out that triangle. Now I have enough information, so many angles. I mean, this is in total 105 degrees. So much information that I could probably set up some sort of trig to calculate. Okay, so let's take a look at tension 1. Tension 1 would be calculated if I can do sine with the opposite side. I got this angle and tension 1. I can find tension 2 because I got the same set of partners over here that I can set up in a sine law. And then I got tension 2 and its opposite angle. Okay, so again, this is just trig from grade 10, all right here. And I got 40.6 newtons for tension 1 and 57.4 newtons for tension 2. I put a little bit of a note at the bottom that says that the greater the angle, so remember one of them had an angle of 60 degrees, would normally have a greater force, and that's what we see. All right, let's go through 2 more examples real quick. In physics, you might have learned it, and I'm not a physics teacher, so I'm just going to try to explain this the best that I can as a brand new calculus and vectors teacher. You can solve things through components, and components means you can break it up into horizontal components, which we denote with a little subscript x, or in vertical components with a subscript y. Okay, so I'm just going to put horizontal and vertical. Okay, so let's show you an example of this. So this means I might not have to draw a triangle, although it seems like triangles are kind of the way to go. Example number 3, Ryan and Selena are pulling a sled with their ropes making angles of 15 degrees and 20 degrees to the line of motion. So if these two people are pulling a sled, that's my sled. Okay, it's like a 5-year-old drew it. It will go in this direction. So this will be my line of motion. Okay, each is exerting a force of 45 newtons. And so that's the magnitude of both of them separately. 15 degrees for Selena, 20 degrees for Ryan. What we can do is we can kind of create a vector diagram. Okay, by drawing these separately and putting them together, tip to tail. Okay, so notice that that's like a theme for this unit. Tip to tail for everything. Okay, and then I have my line of motion for Selena. And since I'm trying to find the force that's pulling the sled, and I know that the sled is actually going to go this way, it's probably going to be both of their horizontal motions together. So Ryan's horizontal motion is actually like somewhere here, but I'm just going to copy that and make it so that you see it down here as well. So the total of both of their horizontal components is going to make the total horizontal force. All right, so let's show you all the numbers and we'll go through it slowly. So the magnitude of this is 45 newtons. Magnitude of this, also 45 newtons. This is 15 degrees. This one is 20 degrees. Okay, so what I'm trying to find is Selena, x. Okay, and I want to know what the magnitude is. I'm going to add it to Ryan's, which is the same as this, really. Okay, so Ryan is going to be r, x, horizontal component. Add them both together, and you get the total movement horizontally of the sled. Okay, so how do we actually do that? Triangles again, break it up. Right angle triangle. Break it up. Right angle triangle. Okay, so showing you the results, it makes a lot of sense to use SOHCAHTOA and not sine law or cosine law. You have right angle triangles, so if you just do the adjacent over the hypotenuse, which is cos, you should get the horizontal component for each triangle. Okay, adding them both together, you get a total of 85.8 newtons for the horizontal force of pulling for the sled. Okay, lastly, example number 4. A 10-kilogram block lies on a smooth ramp inclined at 30 degrees. So here is my ramp. There is my 10-kilogram block that is not going to move, and it's at an incline of 30 degrees. So this is the ground that the ramp is on. What force parallel to the ramp would prevent the block from sliding? So normally it would slide a certain amount and then eventually it'll stop. And so there are several different force vectors acting on it. And I'm going to draw them right now. Okay, so let F represent the force pushing up the ramp. So there is a force going this way. We'll call it this. Required to keep the box still. There's also a force going down, and that is the force of gravity. Okay, so I just put FV for the vertical component. There's lastly a force that actually acts on the surface of the object itself, and it is normal. It's called the normal force, and it is 90 degrees or perpendicular to the ramp or the surface. Okay, so there are these 3 components, and we have to put them all together. So let's take a look at what this would look like if we decided to make a vector diagram. Okay, so we have a force vector that goes like this in this direction. Then we also have the gravitational force vector, which pulls it down. And lastly, we have this guy, which is the normal vector. It's going to pull it this way. And if you think about it, isn't this like the equilibriant? Like all of them together are going in a circle. This box is not moving, so this is an example of an equilibriant vector, okay? Or all of them together creating zero, like nothing's going anywhere. All right, let's make this a little bit more clear so that you get all those marks on a test. This is F, okay? This is FV. All right, and then we know that this guy right here, 30 degrees. Okay, and what else can we draw? Oh, you know what? There was the normal force this way and wasn't in a right angle triangle. So, sorry, I'm saying right angle triangle. I mean just a right angle. I'm going to start to play around with this a little bit. That's 90 degrees. This is a 60 to fill out that rest of the 180, which means this is 30. Okay. And what else can I figure out? Oh, if this is a right angle, I would say that this is probably a right angle too. So that's 60 degrees. Okay, which makes this 30. All right. Okay, so that's a lot going on. Let me erase this a little bit and we can give ourselves a little bit more. That's 60. Now all I need are some numbers around the triangle and we can probably figure stuff out. Okay, so using the weight, the 10 kilogram mass, what I can do is I can figure out the force of the the magnitude of the vertical force. And so this is 98 newtons. Okay, that gives us a little bit more information, so I can find that parallel force, which is what the question asked for. And what I can do is I can say, okay, oh, why don't I go, this is a right angle triangle, right? So if this is 30 degrees right here, and I already have the hypotenuse, I can just use sine opposite over hypotenuse equals to, well, equals to sine 30, right? Okay, so if I solve it like that, I get a magnitude of that parallel force as 49 newtons. So these are many different examples, and yes, they are kind of long. This is a long video, I'm sorry. Now that we're getting into calculus and vectors, it's going to be quite lengthy videos. And so thank you for sticking with me, and I'm going to wish you the best of luck. If you have any questions, comment below.